So our final presentation for the session will be reliability for media patterns and anti-patterns in design and operations. And our presenters will be William Hooper and Hannah Hong from Deloitte Consulting. William is a specialist leader in the media solutions practice at Deloitte. He has over 2 decades experience at the intersection of broadcast media and information technology. Based in Los Angeles, he is a registered professional engineer in California. Hannah is an engineer in the media solutions practice at Deloitte. She is based in New York City. So please welcome to the stage William and Hannah.
Thank you, William. Reliability and availability have always been prime concerns for broadcast and media systems engineers. As much as we'd like to tell you this afternoon how to make any system perfectly reliable with this one weird trick, that's unrealistic. Instead, Hannah and I would like to share some of our experiences at Deloitte as designers and integrators of large-scale, mission-critical broadcast and media systems, and offer some ways to think about reliability problems. We'll briefly sketch the traditional hardware-centric approach to reliability. We'll explain how that approach is insufficient for today's software-intensive complex media systems, and we'll share some potential strategies to build and operate practical systems with good reliability.
So we can start with the IEC standard. So IEC standards define reliability as the ability to perform as required without failure for a given time interval under given conditions. For continuously operating real-time media systems, this is closely related to availability, which is defined as the ability to be in a state to perform as required under given conditions. A failure is the loss of ability to perform as required. So for reliability analysis, many systems having several components can be modeled as series, you can see on the left, parallel, you can see on the right, series parallel, or M out of N systems. If the system reliability is defined as probability RS, with 1 meaning it never fails and 0 meaning it always fails, and the reliability of the components is R1, R2, and so on, then the reliability of a series system in which failure of any component causes system failure is the product of R1, R2, and so on. The reliability of a parallel system in which failure of all components causes system failure is 1 minus the product of 1 minus R1, 1 minus R2, and so on. For M out of N systems, in which failure of more than M of N parallel components causes system failure, the relationship is a little more complicated, and you can see the references on our paper on how to calculate B. Keep in mind the fundamental assumption here. The probability of failure of each component is independent. So for many electronic and mechanical systems and devices, the instantaneous failure rate, or for repairable items, the instantaneous failure intensity over time, has been found empirically to be approximated by this vaguely bathtub-shaped curve. The curve can be divided into 3 regions: an early life failure period, a constant failure intensity period, and a wear-out failure period associated with physical phenomena. There are methods for hardware reliability prediction that use models of individual electrical and electronic component failure rates adjusted for quality requirements and conditions of use. These methods, described in documents such as Telcordia SR 332 and the Military Handbook 217, can be used for new products and in other situations in which actual reliability data are unavailable, and they are concerned only with hardware failures and don't consider failures that are caused by software or by operational or maintenance procedures. Manufacturers publish data sheets that quote a mean time between failures of so many tens or hundreds of thousands of hours, but that's just for the hardware, not the software, nor the functioning of the product as a whole.
Indeed, we've found that the high intrinsic reliability of modern, solid-state electronic equipment and the reliability gained through hardware redundancy are all too often overcome by software failures. By nature, these are likely to be common mode failures, different things failing in the same way. If the same software runs on several redundant units, then a single bug might cause any or all of them to fail. More troublesome are common cause failures, failures of multiple items which would otherwise be considered independent of one another from a single cause, in which redundant units might fail simultaneously or nearly so. This can happen not only when identical parallel units are operating in lockstep, processing exactly the same inputs with the same software, but also in other less obvious situations. Here are some of them. Redundant units that share internal data structures fundamentally aren't independent. For example, firewalls and IP networks are very often installed in redundant pairs. Either unit can handle the expected traffic, and at any time, ideally one is active and the other is in hot standby. Both units have the same software and static configuration, and for efficiency and security, the active unit also maintains in its memory dynamic internal state, such as a table of in-progress TCP connections to allow through the firewall. So the standby unit is ready to take over immediately if the active unit were to fail. Without disrupting traffic, this internal state is replicated continually from the active unit to the standby unit. A weakness of this arrangement, however, is that if a software malfunction corrupts the internal state in the active unit or the data structures representing it, then that corruption and any further malfunctions that fall from it can also propagate between units. We've observed situations in which malfunctions could be resolved only by completely resetting both redundant units simultaneously, clearing out the internal state, but also causing an unacceptable outage. This problem isn't limited to network firewalls. That's just one example. It can arise whenever nominally redundant units share data vital to their operation. For example, an active standby pair of NMOS broadcast controllers or SDN controllers might maintain a shared table of active routes or flows. Exhaustion of processing, storage, communication, and other resources can also lead to failures. Systems can be fundamentally undersized for their workloads at installation, or as workloads grow over time, or they can become undersized after their effective capacity has been reduced by partial failures against which they were intended to be fault tolerant. This can happen when some important dimension of capacity is overlooked in design. For example, after a failure occurs, a system might still have sufficient processing and storage, but inadequate communications for its workload. Failures can also occur when some limited resource is allocated on demand, but not released when no longer needed. Programmers know about memory leaks. Other examples include persistent storage filled with temporary or obsolete data, network receivers that join but do not leave multicast groups, and trunk lines and switching systems that are held and not released. Resource leaks can occur in parallel in multiple nominally independent units. For example, we once encountered a cluster of redundant servers installed at about the same time, each writing about the same daily volume of messages to its internal log files. The scheduled task to purge these files periodically didn't work effectively, and all of the servers ran out of disk space in a critical partition at the same time, causing a preventable, complete outage of the service they provided. Failures can be amplified when systems do not limit their effects and propagation among multiple units, in cascading failures and overloads. For example, we've seen a cascading failure of a distributed service for processing media files. The service had a large pool of processing servers managed by a redundant pair of coordinating servers. There was plenty of capacity and an architecture that looked very fault-tolerant on paper, but the entire service was halted by one media file submitted as input. This file had a specific characteristic that broke any server that tried to process it, a defect in the software. The coordinator server responded to each such failure by resubmitting the file to the next server and the next and so on, cascading into a total outage of the system. Poor response to overloads can also be considered a failure. Sometimes an overload should result in degraded service to all users, but in other circumstances, it's better to exclude some users or offer them no service than to give everyone a poor service. For example, in a packet switch network, when traffic exceeds the capacity of a network link, some packets are likely to be dropped. With TCP/IP, Transmission Control Protocol, drop packets trigger senders, retransmission, and congestion control mechanisms, and reliable data transfers can continue just with lower throughput. Without those mechanisms, or in circumstances in which they're impracticable, as with, say, MTS2025 video flows, which are transmitted at constant bit rate without any feedback to the sender, then an overload that causes dropped packets may result in severe picture impairments in every flow that uses that overloaded network link, a poor response to an overload. To start up, run, and be managed, software-defined media systems often require services. They depend on services from the network or environment. These dependencies may include network services such as DHCP and DNS, PTP and NTP time, and user authentication and authorization with Kerberos, LDAP, or external identity providers. Systems may also depend on broadcast controllers, SDN controllers, virtualization platforms, storage systems, and network or element management systems, among many others. Each of these services, in turn, may also depend on some or all of the other. You can model the overall network of dependencies in a media facility as a directed graph, a series of nodes and edges, and in principle, evaluate it for reliability as a series parallel system or using fault tree analysis, about which more in a moment. We found that these dependency graphs, however, are very installation-specific and are rarely documented or understood comprehensively, especially where dependencies cross between spheres of organizational responsibility. Circular dependencies, in which two or more services or components each cannot start or cannot operate unless the other is available, are an insidious hazard. This can happen due to configuration changes. Suppose two services A and B are installed and operating, neither one requiring the other. And then A is changed to require B, and then sometime later, service B is changed to require service A. Such a circular dependency might go unnoticed until a simultaneous outage of both services A and B, from which neither service can recover until someone manually breaks the dependency, reconfiguring the services.
All right, so time and date dependent failures. Failures triggered by date, time of day, or elapsed operating time are inherently likely to occur on many units at once. Clocks are fundamental to real-time digital media and an essential feature to all but the most simple computers. Internal clocks ticking in milliseconds, microseconds, or at even more exotic intervals help schedule processor workloads and real-time tasks, maintain I/O data rates, and count pixels, samples, lines, and frames. The time of day and calendar drive broadcast schedules, initiate maintenance routines, and validate security certificates, tokens, and software licenses. Such extensive use of clocks and calendars bring vulnerability to time and date related failures. The year 2000, year 2038, and GPS week rollover problems are all associated with specific fixed dates, but malfunctions have also been triggered by elapsed time since startup or installation or by discontinuities in civil time, such as leap seconds and the start and end of daylight time. This can even happen if the device doesn't even care about what time it is. For example, we're aware of a video processor that accepts an analog reference signal. If it contains VITC time code, then the processor output goes black every day when the time code rolls over to 0. The processor doesn't even use the time code for anything else. It's just an internal bug. Changes to software, firmware, and software configurations can affect multiple units simultaneously as well. These situations can arise in cybersecurity and in other contexts. Practical cybersecurity defense and organizational security policies often require prompt installation of software updates to mitigate newly discovered vulnerabilities and continual refreshing of security software to protect against any emerging threats. Such changes, distributed widely and automatically at frequent intervals, with limited opportunities for testing, may provide necessary protection, but they also have some risk. Updated software and security databases have introduced bugs and incompatibilities. They've impaired system performance and caused legitimate files and network communication to be misclassified as malicious and quarantined or blocked. In some cases, computers have stopped working entirely, and such effects are compounded when they occur in many places simultaneously. Day-to-day administrative processes can also have far-reaching effects. If you have a lot of things, it's often handy to have automated systems to manage them, but it also makes it way easier to act more broadly than intended or with unanticipated results. We've had trouble with centralized directory services. We have to hook up the media systems for user authentication or authorization, but unless everyone's careful about it to prevent it, systems intended for corporate IT environments can actually propagate to real-time media systems where they're no good. And nobody wants a locking screensaver on your PC in master control.
With all this bad news, what can you do about it? Still try to build reliable systems. Let's talk about some countermeasures in design and operations. None of these works all the time, and they all have trade-offs, but we'd like to share some possibilities to think about. It's easier to build reliable systems from reliable components, of course, inherent reliability. We're not here to discuss software design and testing in depth, but if you're designing or implementing a product, there's an extensive literature of distributed systems and software engineering. Sometimes, if it's feasible and consistent with other important objectives, you can divide systems into relatively self-contained modules, each having limited, well-defined, robust interfaces with as few common dependencies as practicable. This simplifies reliability analysis and may reduce the risk of common cause failures and the potential effects of single failures. The overall trend in media systems, however, as we've heard just in this session, is towards greater integration and tighter coupling. Yesterday's change of discrete units for videotape playback, switching, signal processing, and video and audio compression, for example, have been replaced by true channel-in-a-box devices, originating several linear channels in one compact server. This trend is generally favorable for cost and efficiency, and to the extent it reduces the number of physical components in a system, it may also benefit reliability. We've found that the right balance between division and consolidation is fundamentally a matter of engineering judgment. This can be informed by more formal methods, and again, more on that later. For the most vital functions, rather than providing only identical redundant units which may be inherently susceptible to common cause failures, you can provide more than one independent implementation, despite potentially higher costs to acquire and support. For example, for playout of high-value broadcast TV channels, we've installed emergency backup playout servers, which accept the same playlists, the same media files, the same live inputs, and produce similar outputs as the servers use normally. But they were supplied by a different vendor and use a different operating system, different control software, and different video and audio codec libraries. So implementation diversity. When mechanisms important to reliability are not exercised by the regular use of a system, you may need to test them at initial installation, as changes are made, and at periodic intervals. The ability to rapidly adapt plans to reality will always be essential in disasters. But one key to an effective response is to have a broad toolbox of planned and practiced actions, thoroughly and regularly validated in advance, and not just ideas on paper. Practical testing requires you to commit resources and accept some risks, of course, but these should be balanced against the potential costs of latent failures or limitations that might not be discovered until the worst possible moment. Some organizations use so-called chaos engineering, a process of introducing controlled random failures into their production environments as an ongoing test of those environments' fault tolerance.
Many media systems could benefit from structured but lightweight processes for configuration management, including documentation of configuration settings, software and firmware versions, and similar important information in a repository apart from the systems themselves. Complex systems with myriad interdependencies also demand more careful pre-planning and organizational communication of changes, including thorough analysis of their potential scope and effects. The ability to roll back quickly to a known working configuration is also quite valuable. Careful planning is needed to get the benefits of more formal practices without introducing cumbersome rituals that will drive up costs and hinder agility. Ideally, every production environment would be supported by a complete lab or test environment with examples of all hardware and software, so you could test every change fully before doing it. If this costs too much, or for added assurance, you might be able to limit the risk of changes by dividing the production environment and changing only one part at a time, sometimes called a blue-green strategy. Suppliers should also be asked to provide detailed release notes or product change notifications with each new release of software or firmware. Unless you know what has changed, it's really hard to evaluate the risk-benefit ratio of installing a new release, and it's hard to figure out what regression testing may be appropriate to confirm that important previously existing functionality has not been compromised. A lab environment is ideal for this, but where maintenance schedules allow, it can be valuable to run a focused suite of regression tests in production right after installing new software or making other changes, with the results determining whether to accept the new configuration or revert back to a previous one.
Getting the full reliability benefit of investments in fault tolerance requires prompt detection, diagnosis, and repair of failures, ideally before they lead to unacceptable operational effects. In complex software-intensive systems, relying on operator reports or manual inspection of displays and indicators is completely insufficient. Instead, you'd really like to have a comprehensive monitoring system with pervasive instrumentation, well-defined alarm thresholds and alerting criteria, and facilities for rapid retrieval and analysis of historical data. A system like that can also collect data for reliability analysis and maintenance planning. Defining and measuring service-level indicators for systems and key technical processes and collecting basic data about all system failures, regardless of scope or effects, can contribute to improvement of system reliability through data-driven decision-making, including identification of adverse trends and assessment of change control and maintenance processes. Some organizations, the largest one, may need a formal failure reporting and corrective action system, FRACS or FRACAS. Others may benefit more from an easy-to-use data collection system with simplified procedures and less extensive documentation. These countermeasures that we've just mentioned on the screen here are some ways we've been able to improve reliability of software-intensive media systems for our clients. We'd also like to share something on system engineering techniques.
All right. For the largest, most complex media system, or if failures could have serious consequences, it may be cost-effective to apply organized methods of reliability engineering to predict system reliability, assess fault tolerance, and evaluate strategies for improvement. There's much more to those than we can really cover here, but we'll mention two techniques, and you can do these for whole systems or more realistically in our industry, just two important parts. In failure modes and effects analysis, you subdivide the device or system into its elements, and based on the requirements for each element, you identify potential failure modes, how that element could potentially fail. For each failure mode, you write down information such as existing methods of detection, control, and prevention, the immediate and top-level effects of failure, the causes, and recommended treatments to eliminate or mitigate the failure mode. You can also add prioritization based on likelihood, consequences, and detectability as well. Fault tree analysis builds a fault tree, which is a top-down visual representation of conditions that could lead to a failure or any other top event. It's essentially a big tree of combinatorial logic with the usual kinds of gates like and, or, and nor, and plus some extra ones that deal with sequential failures. You can include quantitative or qualitative probabilities, and it's important to consider conditional probability and common cause failures as well. These and other formal methods can be time-consuming to prepare and document. But if you have a particularly complex system or a part of a system, and a failure would be a really big deal, then it may be worth it.
Today's software-intensive media systems fail in ways that are poorly characterized by traditional hardware-centric reliability models. Designers and maintainers must also consider software reliability, system reliability. Just adding spare units often isn't enough. But as we've discussed, countermeasures from other industries and system engineering techniques can be applied effectively. We'd be glad to take some questions if there's time. Thank you.
Well, I do have one question from here. The question, and I think everyone thought this one, how often do you suggest that a large network production facility conduct DR testing?
That's a very challenging and complicated topic. I think that it's really something that depends on the system architecture and as we talked about in a system design, to plan for something like that you have the ability to say, do we have segments of the system that we can test, isolate into, or that we can test using another facility. It's really at the largest scale. I think it's very hard to do a full DR test end to end. That just becomes impracticable, given the value of the operation and the disruption that causes, particularly if you have, downstream affiliates receiving, in different companies and so on. But it may be possible to look at testing parts of those, capabilities at a time, rather than trying to do a full on, we're going from the backup facility now test. We're familiar with a client that has, multiple broadcast centers that were designed to back up one another. They've never actually used that capability, but they've exercised parts of it to be confident that it would work when needed.
Do we have any other questions? Seeing none? Thank you both very much.
Thank you.
Thank you.